Hey guys, these are the example problems that go along with chapter 1. So for this first one, that first lecture, we're going to, chapter 10. So for this first lecture, we are going to be doing examples 1, 2, and 3. So for example 10.1, all you're doing is converting units of pressure. We have done so much converting in your past that this should be second nature to you. So it says in part A, convert 0.357 atmospheres to torrs. So we know that there's 360 torrs for 1 atmosphere. We were given atmospheres, so you start with what you're given, put the opposite, or put the same unit on the opposite side. So because this is on top, put 1 atmosphere on bottom. Our conversion factor goes on top, so that you end up multiplying 0.357 times 760 to get that 271. Then it says convert 6.6 times 10 to the negative second torrs to atmospheres. So now you're doing basically the same thing, but in reverse. So we're putting what we're given here, 6.6 times 10 to the negative 2. The conversion factor in this case goes on the bottom because we were given torrs, so torrs need to cancel out. So I'm going to take 6.6 times 10 to the negative 2, divided by 760 to get their 8.7 times 10 to the negative fifth, 10 to the negative fifth. Can't honestly tell, it's very small on my screen. Last one is convert 147.2 kilopascals to torr. So for this one, we know that the relationship is 760 torrs will equal 101.325 kilopascals. So you're going to put what you're given, the 1.47 times 0.2 kilopascals. Our 101.325 kilopascals goes on the bottom to cancel out. 760 torrs goes on top. So what you want to do is multiply first, then divide to get the 1,104 torrs. Alright, so let's see. Go to the next one. Okay, so that was just other practice ones. You guys can give those a try if you would like to, see if you really understand what's going on. Wouldn't hurt. Alright, so using a manometer to measure gas pressure. This is example 10.2. On a certain day, a laboratory barometer indicated that the atmospheric pressure was 764.7 torrs. A sample of the gas is placed in a flask attached to an open-end mercury manometer, as you can see in this figure here. And a meter stick is used to measure the height of the mercury in the 2 arms of the U-tube. The height of the mercury is the open-end arm. On the open-end arm is 136.4 millimeters, and the height in the arm. One second. Okay, just a minor misunderstanding between the kids and the Grinch. We're gonna hopefully move on. Okay. So the height of the mercury in the open end arm is 136.4 millimeters, and the height in the arm in contact with the gas in the flask is 103.8 millimeters. So what is the pressure of the gas in the flask in atmospheres and then in kilopascals? So you're given the 2 different heights and asked to determine the gas pressure. So we need to know that the millimeters of mercury, or mmHg, is a unit of pressure. So if we go to this next one here, you would first want to understand that the pressure of the gas will equal the pressure of the atmosphere plus the height. So our pressure of the atmosphere is 764.7 torrs plus the difference in the 2 torrs that we were given in the previous slide. So you would subtract these first and then add that to get the 797.3 torrs. And then what we need to do is convert the torrs to atmospheres. So we take our answer from this part, divide it by the 760 torrs for 1 atmosphere to get 1.049 atmospheres. And then what we want to do is convert from atmospheres to kilopascals. So you take the answer that we just got for A, so 1.049 atmospheres, and the 1 atmosphere goes on bottom. Our 101.3 kilopascals goes on top. So we multiply the two, and we get 106.3 kilopascals. Another practice exercise is down here, in case you would like to give that a try. All right, so this last example that we're going to do for this one is evaluating the effects of changes in pressure, volume, and the amount of moles, as well as temperature on a gas. So suppose we have a gas confined in a cylinder with a movable piston. So that just means that the volume can change because your piston can go up or down depending on what's going on. Consider the following changes. Heat the gas from 298 K to 360 K, so kelvins, at a constant pressure. Reduce the volume from 1 liter to 0.5 liters at a constant temperature. Inject additional gas, keeping temperature and volume constant. And then indicate how each change affects the average distance between molecules, the pressure of the gas, and the number of moles in the cylinder. So, for A, we're going to increase the heat while keeping the pressure the same. So, pressure won't change. But because you're increasing the temperature, the volume is going to increase. But the number of moles, we're not adding anything, so the number of moles will stay the same. But because volume is increasing, and because you're increasing the kinetic energy by putting in more temperature, then the molecules themselves are going to expand or get farther apart from each other. So for A, we have the distance between the molecules increasing, the pressure staying the same, and the number of the moles in the cylinder staying the same. Okay, so now that Evie's in timeout and Eli is maybe going to join us for this lecture, we can hopefully finish it. All right, so we got A done. B, we are going to reduce the volume from 1 liter to half a liter at a constant temperature. So temperature is staying the same, but because our volume is decreasing, that means that the distance between the molecules is going to also decrease. The pressure of the gas is going to increase because this is an inverse relationship. So volume down, pressure up, and the number of moles is going to stay the same. Be right back again. Okay, hopefully we got that situation sorted out. So I love online learning, don't you guys? It's so great. Okay, part C, we are going to inject additional gas, keeping the temperature and the volume constant. So with temperature and volume constant, your distance between the molecules is going to actually decrease because in the same space we are adding more stuff. So think about this like that social distancing, right? If I go to Costco and there's only 3 of us in the store, I can get as far away from those people as I want, but then if you put 100 people in that store, suddenly I can't get as far away as I want to. So our distance between the gas molecules will decrease. The pressure is going to increase because, again, you're putting more things in that same amount of space. And the number of the moles will also increase. If you have any questions on these 3 examples, please let me know.